your background. So are you all college student or where are you from?
High school graduate.
High school graduates. Good. School, all of you? So I want to keep that level actually, that's what I'm asking. So I should not talk something. You are in engineering college. Okay, good. Okay. Get some ideas. Okay. So I will tell you the story of neutrinos, that is the title of my talk. But before that, let me just, what is this? Is it working? Is this slide changes or is it off? Just check. Off? On? Okay. It works. Where is that? Maybe it is. Okay. So let me start with a quiz. So here are some pictures of some scientists. Some of them are still alive, and there are quite a few of them. So there is something common among these scientists. Do you recognize any of them? Maybe not. So the common is they all got Nobel Prize. And they all got Nobel Prize, so that is a common one, but there is something more common to them. Second one is they got Nobel Prize for working on only one particle, same particle, and that's neutrino. So now let's see, there are so many of them, from 8 of them, they all got Nobel Prize for one particle, neutrinos, and this has never happened. So think of the importance of that particle. There is something more common in that. These guys are all experimentalists. They are all experimentalists. None of them is theorist. So this is also very uncommon. 8 experimentalists got Nobel Prize for working on one particle. Of course, at different times, on different aspects, and so on. So you can imagine how exciting can be that area. So that's something I want to tell you. So before that, neutrino is a particle, elementary particle. So let's look at what are those elementary particles. Okay? Elementary particles means these are like the mortars and bricks for of your structure you built up. So there are what everything is made out of. Okay? So everything means everything that you can visibly see, or the you, me, all this whole world, and the whole the stars and galaxies and so on, they are all made out of these fundamental particles. You won't even know need of them. So now, mostly what is important is these 3 particles. Okay? And these 2 are the quarks. They are called quarks. There are all 6 quarks. The red colors, they are all quarks. And these yellow colors, these are leptons. Somebody was asking the lepton number. So these are the leptons. So they have their unique characters, which I may not be able to tell in this talk too much. But the world that is made out of is really don't need all these particles. What you need only these 2 and this one, right? This up quark and down quark. A proton and neutron is made out of up and down quarks. A proton is made out of 2 up quark, 1 down quark. And a neutron is 2 down quark and 1 up quark inside the neutron and proton. So see, now you have the protons and neutrons just from these up and down quark. So use those protons and neutrons and make the nucleus from hydrogen to thorium and uranium and so on. All the elements that we see, they are all made out of those up and down quarks, the nucleus. And then you put the appropriate number of electrons going around it, and you make the corresponding atoms. Atoms combine, they form molecules and so on. So you only need these 3 important particles. But for some reason, I'm not going to talk about this today, these particles, actually there is not only 2, there are also another sets of 2 sets of 2. So there are 6. And these are called charm, strange, top and bottom. Actually the charm and strange, they are just like up and down. All their properties, they behave exactly the same way. Only thing, they are heavier. top and bottom are also like up and down. Their properties are just same, but only thing they are heavier, even heavier. We don't know why that's, for strange reason, the nature wants to repeat these elementary particles in this way, but it is true. Same thing also here. You see this electron, this is muon and tau meson. This electron, the muon and tau meson, these are the heavier leptons. They are also just like electron, only heavier. But, and each of these leptons, they have a partner particles. They are associated with the corresponding neutrinos. That's what these 3 neutrinos comes into picture. No, somebody says 3 neutrinos, because each of these particles, the corresponding neutrino. This is called electron neutrino. This is called muon neutrino because this is associated with muon. This is a tau neutrino because this is associated with tau. What do you mean by it is associated with electron? That means, say for example, the electron neutrino comes, and if it interacts, it will always produce an electron, never a muon or a tau. If a muon neutrino comes and if it interacts, it will produce always a muon, never an electron or a tau, and same for the tau. So that's what is the difference. You will be able to recognize them, okay, by what they are producing when they interact. Okay, this is one way to look the difference. And of course, these are the carrier of forces, but my talk is nothing to do with that, so I will just avoid that. Okay. So my story is not about these important particles of quarks and leptons that the whole universe is made out of. The story I am going to talk about these 3 neutrinos. Okay. So now, little bit of basics. This probably school students and all, everybody has studied. So good. So this is the radioactivity. You have seen that, radioactivity. You are familiar with radioactivity. Radioactivity means you keep some elements, and some of them like uranium and thorium and so on, they will spontaneously convert to other elements, and in the process they will emit some rays or particles called alpha, beta and gamma rays. What is alpha rays? Alpha rays is just helium nucleus, we know that, and this is all. Gamma rays are just photon, high energy, energetic photon, they are gamma rays, quantum light, and beta. But there is something, this is actually the particles, see this bending has some meaning. See, this is taken when in a magnetic field, and you can see in a magnetic field as if these particles, when a charged particle is going through a magnetic field, it bends because of the Lorentz force. Now you see this bending of these alpha particles, all these alpha particles are bending in the same amount. You look at this picture. The gammas are not bending at all, no bending, it's going straight. Magnetic field is not affecting because gamma is not charged. Only charged particles get Lorentz force, right? But beta particles are electrons or positron, depending upon what it is. But you see, there is a difference between this bending. The betas, they are bending, some betas are bending in large curvature, some are small curvature. Because, so that indicates that the alpha particles, when they are coming out of that nucleus, they have the fixed energy, okay? But beta can come out with different energy. This is the energy spectrum of the beta. That means sometimes beta can come out with a small amount of energy, sometimes it can come out with a large amount of energy. But ideally, they should have come out by the same amount of energy, okay? That's what scientists thought, because alphas are also doing the same thing. They are coming out with the same amount of energy. That means all the betas will have fixed energy, like this. All the betas should come up like that. So why the betas are coming out this continuous energy spectrum? What is the reason for that? So let's go back and look at what was happening. This man did that. Okay, so when a radioactive elements get converted to the another element, what is happening inside? Say for example, a proton inside is getting converted into a neutron, okay? In the process, how do a proton convert into neutron? So one electron is coming out, okay? An electron is coming out, so it's a positive electron, of course, positron, but so positron is coming out of the proton and the proton is becoming neutron. So that is what was happening. So this is actually a two-body process, right? So now the energy difference between these two has to be given to this positron always, because this is so heavy, it doesn't take any energy, almost zero, negligible. So all the energy difference between them has to go to this particle. So if that is so, this particle has to come out with a fixed energy, whatever is the energy difference between these two. That's it. But that is not happening. So why it is so? People are puzzling. People thought, and energy conservation is one of the pillars of science, right? It is, scientific theories are depending on the energy conservation. So is this so that energy is not conserved here? So that was the idea or puzzle people are worried about. And then came this gentleman, Wolfgang Pauli, in 1930. He says that probably this is not what is happening. Maybe along with this positron, there may be another particle is coming out, a neutrino. He gave the name. He didn't call this a neutrino, but anyway, so he called it neutron because neutron was not yet discovered. But so this was the reaction he suggested this is happening. So this is a 3-body decay, and now it is easy, because if it is a 3-body decay, that whatever is the energy difference, part of it will be taken by this one, part of this will be taken by the neutron. Sometimes this guy can take more, sometimes this guy can take more. So that will explain this energy, continuous energy, not this one. So maximum can be up to here. So okay, this was how neutrinos were introduced. However, as you have seen in the previous talk, that it was introduced in 1930s. The neutrino theory came in 1936 by Fermi, Enrico Fermi, but it took long time. Enrico Fermi, while calculating the rate, he found that even if neutrino is existing, it will be very difficult to detect because neutrinos hardly interact. See, whenever an electron is going through your medium, it will interacting all the time, right? And similarly for the protons and so on, they interact very fast. But these neutrinos will not interact very fast. So it will be difficult to detect. But difficult means almost they thought impossible. But then what was happening? They waited for a long time when then suddenly a strong source of neutrinos became available. Because even if it is neutrinos interact very weakly, if you have a large number of them, maybe one of them will interact. Okay, that was the idea. So what do you get this large number of neutrinos? So they had to wait till the Second World War over, because after the World War there was this strong source of neutrinos came into existence. And you know what are those? Those are the nuclear reactors. Nuclear reactors came after the World War. I mean, it was invented during the Manhattan Project and before that and so on, but in the peaceful use of nuclear fission, that is nuclear reactor, came after the war. And when the nuclear reactor came, they saw that this will be the strong source of neutrinos, because it has inside them a large number of neutrons, right? A free neutrons, and neutrons will decay and produce antineutrinos. And that is why they did this experiment. As I think I am not going to talk much about, because the previous speaker has already talked about it. So this is actually a beam. This antineutrino flux came from the nuclear power plant, and then it will be going to the cadmium chloride solution with water, and then it will produce the inverse of this beta decay. That means antineutrino coming out of the nuclear reactor will interact with the proton inside this medium, and it will produce a neutron and a positron. See, just opposite, okay? So it is actually, it's antineutrino plus proton going to neutron and positron. See, positron will immediately annihilate with an electron inside the medium and produce 2 gammas, and neutron will, after some time, will be absorbed by the cadmium, and cadmium will go to the excited state and will return to the ground state with producing gamma. So that means what will be the event? A prompt gamma because of the positron annihilation, followed by a delayed gamma because of the neutron absorption and its de-excitation. So this is the process. It is very nice to see, and they detected that in 1956 in a nuclear reactor in the United States. So it took a long time. In neutrino physics, everything very slow. So you have to have a lot of patience. And as he got in 96, And this gentleman, these two gentlemen, Reines and Cohen, and as previous speaker also told, that only this gentleman got the Nobel Prize, because by the time the Nobel Prize was given, everything is flowing neutrinos, no? So this guy did their experiment in 1956, got Nobel Prize only in 1995. They had to wait a long period to get the Nobel Prize. By the time Cohen died, so Reines only got the Nobel Prize. Okay, so this is how the neutrinos are established. But soon, neutrino research became an exciting area. And they realized that, now before that let me say, so neutrinos coming from nuclear reactor, is that the only thing that is we are talking about? No, there are many sources of neutrinos. In fact, you will be surprised how many sources are there. Let's go through them one by one. So neutrinos from Big Bang. You have all know about Big Bang, how the universe was created. And at the origin, when it was created, it was only fundamental particles and radiation. So that time, along with all other, those quarks and leptons that I showed you, neutrinos are also produced from those original energy that was there. And so those neutrinos are, so after that the universe are expanding, but those neutrinos that created at the time of Big Bang are still there. But only thing that has happened is that they have cooled down. That means their energy has reduced. They have been slowed down, you can think of. Just like the primordial photon. You all know about black body radiation, right? What is black body radiation? Do you know? These are those photons that was created at the original after the Big Bang. Those photons are also with the universe expansion, their energy is very low. So similarly, those neutrinos are also created. But in fact, neutrinos were the first to decouple, and the first thing that came out from that hot soup. But one thing is their number is extremely large. There are 330 neutrinos per centimeter cube of every part of the universe. In fact, you will be surprised, neutrinos are the second most abundant particle in the universe. The most abundant particle in the universe is the photon, that is the black body radiation. Okay? But neutrinos are the second most abundant, 330 neutrinos per centimeter cube. Okay? Imagine that one. So how many neutrinos are there in this room, created during those ancient time, during the Big Bang? Very large. Only problem is their energy has become so low because of the expansion of the universe, is something like 10 to the power minus 4 electron volt. Roughly, you know electron volt? Electron volt is roughly the energy of the atomic transition, roughly of the atomic transition. So 10 to the power minus 4 times lower than the energy involved in atomic transition. Because of this low energy, we don't know how to detect that yet. But we are thinking, the ideas are there, but we have not yet detected. But their number is very large. Then neutrinos from the sun. This you know, how the sun is burning. Okay? Inside the core of the sun, proton is burning. We know that. Hydrogen is burning. What do you mean by hydrogen is burning? Hydrogen is getting converted continuously into helium nucleus. That means protons are getting converted into helium. That means two of the proton, helium has 2 proton and 2 neutron. So this 2 proton must have been converted to neutron. And when proton get converted to neutron, you will get this neutrinos and these particles, okay? Positrons and neutrinos, okay? So these neutrinos are always created in the core of the sun. And these neutrinos are actually much energetic, much more energy than the electron volt. This is 10 to the power minus 4 electron volt, whereas these neutrinos are much energetic. Something like, few tens of, it can be up to few tens of MeV, something like 20 MeV. Okay? This is a million electron volt. Okay? The difference between this to this is 10 to the power 10. This is 10 to the power 6 and 10 to the power minus 4. 10 to the power 10 orders, magnitude higher, much higher energy. And these neutrinos has been detected. Ray Davis did the experiment, and he was in that my list of pictures that you saw. His picture is also there. He got the Nobel Prize for finding neutrinos coming from the sun. And that is how it is. Then there are this is the sun is a star. When the star ends its life cycle, then it may explode if it is heavier. If it is something like 2.5 times heavier than the sun, then it can explode into a supernova. So suddenly in the night you can look at the sky and suddenly you will see a bright star appear where there were no star earlier, because a star was exploding at that time, and when it exploded, it produced for a very short time large number of neutrinos. Those are called supernova neutrinos. Those are also detected. Then atmospheric neutrinos. You know the cosmic rays. Cosmic rays is coming and hitting our atmosphere. And when they're hitting our atmosphere, they produce some particle called pi meson. And those pi meson are short-lived. They immediately decay. When they decay into a muon and a muon neutrino. And those muon also will decay after some time and produce muon neutrino, electron neutrino, and so on. So a proton, pi meson, but at the end you will get lots of electron neutrino and muon neutrino. So these are much energetic neutrinos, and they are going also through you all the time. So then there are other neutrinos also. I am not going to all these sources. You can also create neutrinos. We also see that, for example, man-made, these are all nature, right? Man-made neutrinos. Those reactors are built by ourselves. They produce neutrinos. Or even accelerator, particle accelerator, they are also producing neutrinos. Now let's look into how many neutrinos we are talking about here. Okay? Now you have already confused that so many neutrino sources. What's happening? So let's see. Every second your body receives about trillion neutrinos from the sun. Your body, every second, trillion neutrinos produced by the sun is going through your body. Every second. 50 billion neutrinos from all the natural radioactivity around the earth, in the earth. You know, however, there are radioactive material, uranium, thorium, in the core of the earth. Neutrinos cannot be stopped, so they will come out from the core of the earth also. They can come out of the core of the sun. So they are also going through your body. Then 10 to 100 billion neutrinos from all the nuclear plants around the world. They are going through your body. Imagine how many neutrinos are going through your body all this every second. Okay? Not only that, it is not only that, you are all producing neutrinos. You are all producing neutrinos. Because your body, every human body has something like 20 milligrams of potassium 40. Some less, some more, okay, depending upon your weight and so on. So that means how many neutrinos? This potassium 40 is radioactive. So your body has those radioactive element. Okay? You like it or not, it is there inside your body. And how many neutrinos you emit? You emit on average 340 million neutrinos per day. Each of you are producing 340 million neutrinos every day. And they are coming out of your body and going at the speed of light to the end of the universe, because it will be very difficult to stop neutrinos. So you must be scared by that time, thinking that all these millions of billions and trillions of neutrinos are going through your body. But rest assured, you are all safe. And you are all safe because neutrinos has to zip through. Don't count the zeros. There are some 20 zeros or 18 zeros. So many people next to each other, then only you can stop a neutrino. So this is a good news for you people, because you are all safe, but this is a bad news for neutrino hunter, people like us who want to detect neutrinos, because if it cannot be stopped, how you are going to detect? And that's why is the problem. And that's why all the neutrino detector in the world has to be very big to detect at least few of them. Huge. So that is the problem, but we have solved that problem. Now let me this is that Ray Davis did that experiment, that inside the sun, 4 protons getting converted into helium nucleus and producing neutrinos, and they did the experiment that how can you detect these neutrinos, because these neutrinos can come and can interact with chlorine 37 and produced argon 37. And this gentleman is Ray Davis. He did that experiment and really detected those neutrinos coming from the sun. Okay, so this is his experiment. He put something like a huge container of this C2Cl4 liquid inside a mine below underground, about 1.5 kilometer underground, and he was in that one. The neutrinos are coming from the sun and sometimes hit the chlorine 37, convert into argon 37. Every month he will count how many argon 37 has been produced. It was a difficult experiment. Only chemists can do such an experiment because you have to separate out few argon atom from a big amount of chlorine. So this is a very difficult, only chemistry can do. But he did that experiment and he saw neutrinos coming from them. Okay, here is his experiment. There is also another experiment, Kamiokande, somebody was talking about Cherenkov detector. This is actually a Cherenkov detector. This is a Cherenkov detector. See how it works? So in that water, so let's say a neutrino comes here. A neutrino cannot be detected directly because it's a neutral particle. Only charged particle you can detect. So a neutral particle neutrino, but it comes, and I told you, if it is an electron neutrino, what it will produce? What particle it will produce? Exactly, it will produce electron. If it is a muon neutrino, it will produce a muon. So this electron neutrino will come, and then a electron is produced at this point inside the water. Now electron, while going through water, okay, it will produce Cherenkov light. In the water, the velocity of the electron is less than the velocity of light in water. Okay? So that is the criteria for Cherenkov light. You can study that. The velocity of that particle has to be less than the velocity of light in that medium. Then only Cherenkov radiation will be produced. Okay? And that was happening here, and they will produce at a cone. You know, a particle is going like that and with a cone. And that angle, what is the angle of that cone? Theta will depend upon what is the refractive index of that medium. Okay? But sometimes it can be small, sometimes it can be large. Anyway, so now it is producing this cone of light. Cone of light means only in the ring, along the ring. So now you put a water, huge amount of water. This is a detector which has something like 40 meters in diameter and 60 meters in height. Okay? And then all surrounding the wall, you put photo detector. These are all photomultiplier. You can see there are 10,000 of them. Imagine much bigger than this room, a cylindrical container, water, swimming pool, and all the wall just putting those photo detectors. Now a particle comes, it hits, produces this light, and it will only hit those photo detectors, not all of them, where the light is going, right? So a ring of photo detector will be detected, and then which photo detector has been hit, how much light has been collected. From there you can find out the direction from which the electron is coming. You can find out, and then you can point them, and then look at it is coming from the sky. Which direction? Is there a sun that direction? And if it is so, it is coming from the sun direction. And they found this is actually all the angle. Okay? In the sky you look at all direction, and this is sun. This is the sun direction, let's say cos theta equal to 0, cos theta equal to 1, theta equal to 0. So when you are looking into other direction, not many are coming. But you see from the sun direction, a large number of those neutrinos are coming. So that tells you that they are coming from the sun, and that's the detected. So they are all detected neutrinos. So what is the problem? Sun is producing neutrinos, you have detected neutrinos. What is the problem? Fine. Problem came, these detectors, so this is what was predicted. You know the sun luminosity of the sun. You can measure by other method. If you know the luminosity of the sun, you can calculate how many neutrinos it will produce. Okay, that is simple. Now once you do that, then what they saw, that they are expected this many neutrinos, and what they measured is the blue, this many neutrinos, much less. All the experiment they are doing, they saw less number of neutrinos. So how come it is so? Is the sun is not that bright? Then it can produce less neutrinos. But no, sun is bright. So it should have produced these neutrinos, but then this became a big problem, that we are getting neutrinos from the sun, but not enough to explain luminosity of the sun. Okay. So then how to solve that problem? And that problem can be two ways, that either the core temperature of the sun is lower, that will affect the neutrino production, less neutrinos will be produced. But the people who are dealing with the sun, who understand the sun better, they told no, that is not possible. Then what is the solution? Then the solution can be something to do with the neutrinos. Let's say neutrinos are produced and something happens to them before they reach us. Then we will not detect them. right? So that may be happening, maybe some of the neutrinos are disappearing. So that disappearance of neutrinos were solved by this neutrino oscillation. What is this? Okay. So now, what is neutrino oscillation? So this was, let me just put it this way, here in one transparency, I am not going to take, that this neutrino, these are the electron neutrino, muon neutrino. They are called, this is called flavor eigenstate, because electron neutrino is associated with electron flavor, muon neutrino is muon flavor, and tau neutrino is tau flavor. So they are flavor eigenstate. And this other, there may be mass eigenstate. These are called nu1, nu2. Let's say the mass eigenstates are different than the flavor eigenstate. Then in quantum mechanics, you have not studied that, little bit of I will tell you that you can, so electron state is a mixture of these two mass eigenstate, different mixture. A muon state, muon neutrino is a mixture of the same eigenstate but different way. This can be happen in a coordinate system. See, if you have x and y coordinate, if you rotate your coordinate system, then you will have a new coordinate, right? xy, instead of that, x prime, y prime. And how do you find x prime? Take projections. And it is exactly that. If you just see cos theta, sin theta, minus sin theta, cos theta, those projections, exactly that. But what is happening now, because but in the core of the sun, when the proton is getting converted to neutron, they are only producing electron neutrino, nothing. No nu1, no nu2, no nu mu, electron neutrino. Okay, this is clear electron neutrino. But this electron neutrino is a mixture of mass. Now, because then when they are propagating from sun to earth, they picked up each of them after some time this factor called, this exponential factor called phase factor. And because of that, when they reach earth, some of them get converted into a muon neutrino. So oscillation comes from there. So you start with electron neutrino, after some time some of them get converted into muon neutrino, after some time again they convert to electron neutrino and so on. So it goes oscillating from one state to another. Now, okay, but why we see less? Because when in the detector we are looking for electron neutrino only, not for muon neutrino, not for tau neutrino. So if some of them got converted into other, we will not detect them, and that's why they are seeing it less. So they solved that problem. They did another experiment. They set up an experiment in Sudbury in Canada, where they can, this is heavy water. Instead of water, they use the same Cherenkov detector, but instead of water, they took deuteron, D2O, heavy water, you know. And heavy water has the properties that it can detect all three neutrinos. And once they did that experiment, just to make short, this is the experiment they got. See, these are the earlier experiment. Now you see, expected and observed agrees nicely. So that means this established that neutrino oscillations is the reason, and that is why they got Nobel Prize for that. So you are getting more and more Nobel Prize. Okay. And then, of course, the atmospheric neutrinos. So these atmospheric neutrinos also, as I told you, they are created in the Earth atmosphere. So they are producing mostly muon neutrinos. So then they have set up an experiment underground, that Kamiokande, that with water Cherenkov, which detected the solar neutrinos also, and they are detecting neutrinos, and they also found that these neutrinos are also reducing their number, muon neutrinos. So they also found, so in the solar neutrino, they showed that electron neutrino oscillates. This experiment shows muon neutrinos oscillate. So that means it is a general phenomena for all neutrinos, and they got Nobel Prize for that. In fact, these atmospheric neutrinos has a India connection, because the atmospheric neutrinos were first detected in an experiment in India at Kola gold field near Bangalore. If you know that, it is now dead. I mean, the mines is closed in 1992, so there is nothing, only water. But in the 60s, that was a very active place of research there. And then they detected, setting up experiment, they are the first to detect these atmospheric neutrinos. And today, this field has grown up into a big area of research. So in fact, we are the pioneer in that way, in that one. And this is one of the experiments done in KGF. And you know, this is a neutrino in KGF, in Kolar Goldfield we have detected. You can clearly see. something is here and suddenly it's giving those tracks. Because the neutrino has come, and neutrino is a neutral, it has interacted and produces a muon and some pi mesons. And there are two views of that. And this can detect those, we have detected those events later also in that experiment, many of them. But only thing is that our detector was not big enough to even study that kind of oscillation phenomena. Okay? But so you can do that in India also. Yeah. So this is about, so now what is, so let's talk about, I will not go through this. So now what, I will tell you what is remaining to now. Now we know that, maybe this transparency should be useful, yeah. So we know that there are three mass eigenstates. That nu1, nu2 I am talking about, those are mass eigenstates. And there are three flavor eigenstates. Now three mass eigenstates, they have their fixed mass. What we do not know yet, that they have nu1, nu2 and nu3. We do not know whether the nu3 is the heaviest of the three neutrinos or it is the lightest of the three neutrinos. Okay, this means mass is increasing this way. So this is the lightest, this is the heaviest. So we do not know whether the nu3 is the highest or, this is called neutrino mass ordering. So what is the ordering of the mass, how they are ordered. So this is one question, this is still unresolved. And this India-based neutrino observatory, that is which is the part of this Vigyan Samadham here, is one experiment that was planning to detect this neutrino mass hierarchy. Okay, the INO experiment. So this is the context where we are here and giving this talk even. Okay, so this is what it is. And then, but there is other problem of neutrino physics. There is something called charge parity violation, CP violation, that the matter and antimatter asymmetric. We know that in our universe there is only matter, no antimatter, right? We only see matter. If it was antimatter and matter in the same number, we would not have existed. But it is good that we don't have much antimatter, only matter. So because we can exist, because at the creation, but we know when the universe was created at the Big Bang's time, the matter and antimatter were at equal number. They are equal. So the question comes, why? What happens to the antimatter? Why do they disappear? Why do they disappear? So this question can be addressed by probably studying what you call the CP violation in neutrino physics. The CP violation is the charge parity. This is actually matter and antimatter, there is a difference. It says actually, if the CP is like some conservation law, okay? CP conservation law, assume that. There is energy conservation law. There is a mass conservation law. Mass has to be constant, all mass. There is conserved. Energy is conserved. Angular momentum conserved. These are certain conservation law. Similarly, the CP was thought to be conserved, but this quantum number appears to be violating. And we know that it is violated. But if it is violated by the neutrinos also, then we can explain these matter-antimatter asymmetries of the universe. Let's not go into theory, but we have to understand whether neutrino and its antiparticle, antineutrino, behave differently. If they behave differently, that means CP is violated in the neutrino particles. And if it is so, that we can use that information to explain what happens to all the antimatters of the universe. So this is a very deep question, but we have to first detect whether the CP is violated in the neutrino sector. So there are many experiments are coming up. Actually, this is in Nature few years back. They talked about 4 experiments in the world that will address these issues, that neutrino sector. What are those? Like neutrinos mass ordering and the CP violation, matter-antimatter asymmetry of the universe. These questions will be addressed by 4 experiments in the world that is coming up. And if you read there, this is Zuno, this is in China, this is an experiment using reactor neutrinos. This is INO, this is the Indian experiment, and this Zuno and INO, these 2 experiments is designed to answer that the mass ordering, that which of the neutrino is the lowest mass, which of the neutrino of the highest mass, that question. And then there are 2 other experiments. One is, these are accelerator based, one is DUNE, this is deep underground neutrino experiment, Stanford. This is where in United States and this is called Hypercam. The Cherenkov detector I showed you underground, water Cherenkov, much bigger than that. That detector is 50 kiloton. This is something like 500 kiloton detector, two of them. That's why called Hypercam, much bigger than Kamiokande. Hypercam. These two detectors is specifically designed to address that CP violation question, then whether neutrinos or antineutrinos are same or different. So these four experiments together will be able to solve all the question related to the neutrino physics, that is oscillations, properties and so on. And a very important question. So we could have been part of this experiment, but probably you know that INO is stuck for other problem. There are some activists there. They are telling to the farmers there, where you want to do this experiment, that neutrinos are bad, they will make your crop disappear, the child will born this, there are all sorts of nonsense they are spreading, and some politicians also have joined them for their own interest. So the experiment is stuck. We are not able to make the underground cavity that we need, but this would have been great thing for the science students of the country if it happened. This is actually this Fermilab experiment. We are not creating neutrinos. We want to use those atmospheric neutrinos that I talked about. They're there. They're free. So we wanted to use those neutrinos in our experiment. But in Fermilab, the DUNE experiment, deep underground neutrino experiment, they are actually sending a neutrino beam in an accelerator here. They're producing, and through the ground, underground, they are sending it to a detector underground, which is something like 1,500 kilometers away in South Dakota. This is, if you know the geography of United States, this is in Chicago, and this is somewhere in the closer to the west coast, not exactly west coast, but in that South Dakota, 1,500 kilometers away. And this is also the underground site where Ray Davis did his solar neutrino experiment, that original where he was doing. So that laboratory space is available. I mean, you have to make a new laboratory, but all the facilities are there, so they are doing this experiment. This is that Hypercam. They will put two detectors, each one of them 500 kiloton, 520 kiloton, and this will be able to do, this will be in underground again. All these experiments underground, because neutrino interaction is very, very rare. So you should do an experiment where there is no other disturbance, no other background, which may mimic a neutrino event. If you do the experiment on the surface of the Earth, then many cosmic rays are coming and interacting inside your detector, and some of them will look like a neutrino event. So to reduce that, you go underground where the cosmic rays get absorbed in the rock overburden, and then you can do this experiment. That's why it is underground. Okay. So this is the Juno. Again, this will be a 20 kiloton liquid scintillator detector in China. They will get the neutrinos from a reactor. You see, you can all sorts of sources. We want to use our INO experiment using atmospheric neutrinos. Juno wants to do their experiment using reactor neutrinos. Fermilab wants to do their experiment using the accelerator produced neutrinos, and so on. So you can have different kind of source, but it will be same basically. And then this is the INO. So we wanted to go under a mountain because the Kola gold field is not available to us. In 1992, the government decided that there is no gold available, so they can't continue to mine there, and they can't maintain the mines. So they have stopped mining, and because of this, whole place is underwater, very difficult to go there. So we wanted to make a small tunnel, 2-kilometer tunnel under a mountain, and below that peak, you will get enough overburden so that all the cosmic ray background can be filtered out, and you can do this experiment. This is a magnetized detector, is a 50 kiloton. There are 30,000 of certain particle detectors you will be building, all the associated electronics and so on will be set up. Probably somebody will be giving a talk on those aspects in this week here, and it will be a beautiful experiment for us to do, and most importantly that the students could have done their, in their own hands, setting up such a beautiful experiment. But I don't know when it will come. Anyway, there are also, as I told you, neutrino detector has to be big. How big? Let me just end my talk by giving you a glimpse of the biggest detector, neutrino detector, that the people have made so far. And this is a kilometer cube size detector. You probably heard the name of the detector. It is called IceCube, and it is located at South Pole under 1.5 kilometer ice thickness. Okay, So they have this detector. So this is actually their control room on the south pole, where they have all the electronics and all the cables are coming from this ice, from the under ice, and then they are getting sorted out here. And the detector is something like, so they make hole in the ice, and they put strings of photomultipliers, this detector that will detect light below. Okay, there are many such strings, hundreds of strings, and they start this. The photomultiplier starts at a depth of 1.5 kilometer, and they go up to 2.5 kilometer roughly. So this place they put some many strings of photomultiplier, and they are all looking down. And then whenever a particle, neutrino, comes from the other side of the earth and then interact in the ice, they will produce those muon or electron. If it is a muon neutron, it will produce a muon. If it is electron, neutron, electron. And when the muon or electron will try to go through the ice is just like water, it will also produce Cherenkov light. And those Cherenkov light, like this, will be detected by those photomultipliers, some of them, and then looking at the heat photomultiplier, they can find out which direction the neutrinos are coming from. This experiment is mostly to look for very high energy neutrinos and point them in the sky, which direction they are coming, to find neutrino source. Okay? If they find neutrino source, that will be also the origin of or the cosmic ray source, and these are the importance. So these are different experiments that is coming up in neutrino physics. Okay. Even underwater, in the Mediterranean, they are putting those string of photomultiplier underwater. At the bottom of the sea, they are anchored, and you see the string of just water, go there and put their photomultiplier. Of course, you have to bring the cables up surface in a control room, collect the detector. And this is also, this is called KM3 net, and this is also coming up in the Mediterranean, just like that. So this is also some, several kilometer cube size detectors. So these are all detectors. Now let me end with this one, which I always do. Why India should, we have faced that question, why India should do an experiment like neutrinos, and what is the purpose? There are many reasons. See, for example, of course, you will solve the question of mass ordering. It is an important science question, and we are inquisitive. We want to know answer, because human race has come up to this stage because we always ask questions and try to find answer. In the process, we develop technologies which become helpful for the society. So of course, our primary interest was to do neutrino physics. We want to answer, we want to solve this very important question, neutrino mass ordering. But in the process of doing that one, we'll be doing many other things. We'll develop various cutting-edge technologies. The massive 50 kiloton magnet that we need there, the 30,000 particle detector that I told you, all those things, the sophisticated state-of-the-art electronics, data acquisition system, and so on. Science students across the country will have the opportunity to participate building each of these components from scratch. Many are already doing it. It will create an ambience of doing things in your own hand, a culture that is missing in India. Second important point is, it's a collaborative science project. It's no single institute can have the ability and resources to do it alone. So we'll be combining with 25 research institutions, IITs, they will be all doing. Some of them will be working, developing detectors, some may be working electronics, some engineering institute can participate, in fact is participating in such things, some working on various engineering aspects, some are optimizing detector using computer simulation, writing software and so on. Culture of collaboration and cooperation is another benefit that will emerge from such mega science project, and why the mega science projects are important. Okay? Thank you. Yeah, there are some questions. Okay, let me start from back. Yeah.
So you said there is a cyclical change between an electron neutrino and a muon neutrino.
There is a
cyclical change between an electron
oscillation. Yeah.
So why is the tau neutrino not a part?
Of course, the tau is part. I just gave you two examples. Actually, so if I show you, that's really, I have. Okay, so there's just, since it's a good question, you have. Okay. So I gave this example just to explain to you. I gave this example only to explain to you in terms of two. It is simple to understand, no? But now you think of three coordinate system rotating, and that has been explained here actually in this picture here. I have not talked about those because those are some details. Here, see here. Here is the nu1, nu2, nu3 is the mass eigenstate, and electron neutrino, muon neutrino, tau neutrino, they are the favor eigenstate. They are all there, and this is the mixing matrix. All those sin theta mixing angles are all in this. And this is there are now more mixing angles, not one. There are 3 mixing angles. They are called 1, 2, and 2, 3, and 3, 2. And they are there, so on. And because there is a 3 by 3 matrix, that's why there is this CP violation also will be there, inbuilt into this. All those are there.